Here's the formula for the volume of a sphere. Differentiate. It's the formula for the surface area. This is the area of a circle. Differentiate. It's the circumference. Then, this is the volume of a cube. Differentiate. Is that the surface area? Each face has area r squared, so the total surface area is 6r squared. They don't match. Why does this beautiful rule, differentiate volume, get surface area, work for spheres, but seem to fail for cubes? This leads us to the question of what calculus is fundamentally measuring. First, let's prove why this rule works for spheres at all. This is the area of a circle with radius r. Now, increase the radius by a tiny amount delta r. The new radius is r plus delta r. Let the increase in area be delta s. Delta s is the area of the larger circle minus the area of the original one. If we simplify the expression, delta s equals 2 pi r delta r plus pi delta r squared. Now divide both sides by delta r. Let delta r go to 0. This term disappears. What's left is 2 pi r. So the derivative of a circle's area is its circumference. The same idea works in 3 dimensions. The derivative of a sphere's volume is the surface area of a sphere. In fact, this goes much further. If you differentiate the volume of an n-dimensional sphere, you get the surface area of that sphere. But cubes seem to be a problem. Differentiating the volume of a cube is not the same as the actual surface area. Does the cube break the pattern, or are we missing something? We are missing something, the reference. With circles and spheres, the shape is naturally described by distance from the center. Every point on the boundary lies at the same distance r, and changing r shifts the entire boundary outward uniformly. This radial parameter is exactly what we integrate over when computing area and volume. Now, let's apply the same principle to a cube. Here's the center of the cube. Let r be the distance from the center to each face. That means the full side length is actually 2r. With the definition, the volume of the cube is 2r cubed. Differentiate, you get 24r squared. Now, check the surface area. Each face has area 4r squared, so the total surface area is 24r squared. This time, the numbers match perfectly. The cube didn't break the rule. You were just measuring it the wrong way. We can see the same trap in 2 dimensions. Take an equilateral triangle with side length a. Its area is this. Differentiate with respect to a. It's not the same as the actual perimeter. Once again, we are missing the right reference. For an equilateral triangle, the matching radius is the inradius r, the distance from the center to each side. In this case, the side length is this. Now rewrite the area in terms of r. Differentiate with respect to r. Compute the perimeter in terms of r. This time, they match exactly. Even for an equilateral triangle, the derivative of the area is the perimeter. One last step. Differentiation and integration are inverse operations. So, if differentiating the volume gives surface area, integrating surface area should give volume. From the circumference of a circle to the area of a circle, from the surface area of a sphere to the volume of a sphere, from the surface area of a cube to the volume of a cube. Surface area and volume aren't separate ideas. They are two sides of the same structure, connected through differentiation and integration. Once you choose the right way to let a shape grow. Thank you.